we are going to explore how modern engineers build intelligent systems that can check, that can think, see, and speak. Before we dive into the details, let's understand what this entire presentation is about. The subtitle itself tells us the journey from data to deployment, which means we will be covering everything starting from how raw data is collected, all the way to how a finished AI model is deployed and used in real world applications. You will notice three important terms mentioned on this slide: neural networks, generative AI, and MLOps. These are not just buzzwords, they represent three major pillars of modern AI engineering. Neural networks are the mathematical structures inspired by the human brain that allows machine to learn from data. Generative AI refers to systems like ChatGPT or image generations that can create new content, text, images, code, or video, rather than just analyzing existing data. And MLOps is the practice of managing, deploying, and maintaining machine learning models in production, similar to how DevOps work for regular software. Throughout this presentation, we will explore each of these ideas in depth. So keep watching till the end to get a complete understanding of AI engineering as a career and as a discipline. Let's start with the basics. What exactly is AI engineering? In simple terms, AI engineering is the discipline of designing, building, and deploying intelligent systems that learn from data and make decisions on their own. Think of it this way: a data scientist might build a brilliant model in a research notebook that predicts customer churn with 95% accuracy. But that model is useless to a business until someone takes it out of the notebook and turns it into a real working product that millions of users can access reliably. That someone is the AI engineer. This role essentially bridges the gap between the data science models, which are often experimental, and a research focused and production software which needs to be fast, stable, and scalable. AI engineering is what powers the everyday technology we use without even realizing it. When you search something on Google, when Netflix recommends a show, when your phone's voice assistant understands your command, or when a self-driving car makes a split-second decision, all of this is powered by AI systems built by AI engineers. And because AI is being adopted so rapidly across every industry, from healthcare to finance to e-commerce, AI engineering has become one of the fastest growing and most in-demand careers of this decade. If you are watching this video to understand whether this field is worth pursuing, the short answer is yes. The demand is only going to increase from here. Now let's go one level deeper and understand what artificial intelligence actually means. Artificial intelligence, or AI, is the science of making machines mimic human intelligence. That means giving machines the ability to learn from experience, reason through problems, and solve tasks on their own, just like a human would. This might sound abstract, so let's make it concrete with examples you already interact with every day. Take voice assistants like Siri and Alexa. When you ask them a question, they are using AI to understand your speech, process the meaning behind your words, and generate a relevant answer. Next, think about recommendation systems. When Netflix suggests a movie you might like, or Spotify creates a playlist based on your taste, these platforms are using AI algorithms that have learned your preferences from your past behavior. Then there are self-driving cars which use AI to see the road through cameras and sensors and react in real time to pedestrians, traffic signals, and other vehicles, a task that requires extremely fast decision making. And lastly, spam filters in your email. This use AI to automatically sort good, legitimate emails from junk or spam messages, saving you the trouble of manually checking every single email. So, in essence, whenever you see a machine doing something that would normally require human judgment or perception, that's artificial intelligence at work. Types of AI. Artificial intelligence is not just one single thing. It is actually classified into different types based on how capable the system is. This ranges from the AI tools we use today, which are quite limited in scope, all the way to a hypothetical superintelligence that doesn't exist yet. Let's break down these three types one by one. First, we have narrow AI, also called ANI or artificial narrow intelligence. This is the AI that exists today and that we interact with constantly. Narrow AI is extremely good at performing one specific task. For example, a chatbot is great at answering questions, but it cannot drive a car. Face unlock on your phone is excellent at recognizing your face, but it can't recommend a movie. So, narrow AI powers things like search engines, chatbots, face unlock, and recommendation systems, but each of these systems is specialized for just one job. This is our current reality. Second, we have general AI or AGI, artificial general intelligence. This refers to a machine that has human level thinking ability across any task, not just one specific job. AGI would be able to learn a new skill, reason about unfamiliar problems, and adapt just like a human brain does. This is actively being researched by companies and scientists around the world, but it has not been achieved yet. We are still in progress towards this goal. And finally, we have Super AI or ASI, Artificial Superintelligence. This is a theoretical concept where a machine's intelligence would completely surpass human intelligence in every aspect: creativity, problem solving, emotional understanding, everything. This remains a future and hypothetical idea, something you'll often see discussed in science fiction and AI safety research. But it is not something we have built or even fully understand how to build yet. One of the most common confusions for beginners is understanding the difference between AI, machine learning, and deep learning. People often use these three terms interchangeably, but they actually represent a nested relationship like circles inside circles. Let's clarify this. At the outermost level, we have artificial intelligence, which is the broad goal of making any machine act smart, meaning it can perform tasks that would normally require human intelligence. This is the umbrella term that covers everything inside AI. We have machine learning, which is a subset of AI. Machine learning refers specifically to systems that learn patterns from data, rather than being explicitly programmed with fixed rules. For example, instead of writing thousands of rules to detect spam emails, we simply feed the machine thousands of examples of spam and non-spam emails and it learns the pattern on its own. And finally, inside machine learning, we have deep learning, which is a further subset that specifically uses multi-layer neural networks. Networks with many layers stacked on top of each other to learn extremely complex patterns from large amounts of data. Deep learning is what powers things like image recognition and advanced language models like ChatGPT. So remember this hierarchy. AI is the big goal, machine learning is one major approach to achieve that goal, and deep learning is a specialized and more powerful technique within machine learning. Now, let's talk about what an AI engineer actually does on a day-to-day basis. Because this job involves much more than just building models. There are five key responsibilities that define this role. The first responsibility is to understand the problem. This means taking a business goal like reduce customer churn or detect fraudulent transactions and translating it into a well-defined machine learning task that can actually be solved with data. The second responsibility is to prepare data. This involves collecting raw data from various sources, cleaning it to remove errors and inconsistencies, and labeling it correctly so that the model has accurate examples to learn from. This step often takes up the majority of an AI engineer's time because messy or incorrect data leads to poor model performance. The third responsibility is to build and train models. Here, the engineer chooses the right algorithm for the problem, whether that's a simple regression model or a complex neural network, and then tunes its parameters to get the best possible performance. The fourth responsibility is to deploy and integrate the model. This means taking the trained model and shipping it into real applications and APIs so that actual users and systems can use it, not just leaving it as an experiment on a laptop. And finally, the fifth responsibility is to monitor and improve. Once a model is live, the engineer must continuously track its accuracy over time because real world data changes and models need to be retrained periodically to stay accurate and relevant. So, an AI engineer is not just someone who builds model, they own the entire journey from problem to production. Building an AI system is not a one-time task. It follows a repeatable pipeline or what we call a life cycle, where each stage feeds into the next and the whole process loops back for continuous improvement. Let's walk through these six stages. The first stage is problem, where the team clearly defines the goal, what exactly are we trying to solve or predict. The second stage is data, where the team collects and cleans the data needed to solve that problem. The third stage is model, where the engineer picks an appropriate algorithm suited to the problem and the data available. The fourth stage is training, where the chosen model actually learns from the data by adjusting its internal parameters to minimize errors. The fifth stage is evaluation, where the team tests the model's accuracy on data it hasn't seen before to make sure it will perform well in the real world and not just memorize the training data. And the sixth and final stage is deployment, where the model is shipped out to actual users. But here's the important part, this is not a straight line that ends at deployment, it's a continuous loop. Once the model is in production, it is constantly monitored, and as data arrives over time, the model is retrained to keep it accurate and up to date. This loops is what makes AI systems continuously improve rather than becoming outdated the moment they are deployed. Every profession has its toolkit, and AI engineering is no different. This slide covers the everyday stack, the tools and the technologies that an AI engineer uses to build, train, and understand data. Let's go through each one. First is Python, which is the core programming language for almost all AI work. It's popular because of its simplicity and its massive ecosystem of AI and data science libraries. Next is TensorFlow, which is Google's deep learning framework, widely used in the industry for building and training large neural networks, especially in production environments. Then we have PyTorch, which is Meta's flexible research framework. It's particularly popular in the research community and among engineers who want more control and flexibility when experimenting with new model architectures. Next is NLP or natural language processing, which is not exactly a tool but a field of AI focused on understanding human language. We'll cover this in more depth in an upcoming slide. Then there's computer vision, another major field within AI focused on reading and interpreting images and video. Again, something we'll explore in detail shortly. And finally, we have scikit-learn, which is a Python library used for building classic machine learning models like linear regression, decision trees, and clustering algorithms. It's usually the first library that beginners learn because of its simplicity and clean interface. Together, these six technologies form the foundation that most AI engineers build their careers on. Now, let's understand how machine actually learn because this is one of the most fundamental concepts in this entire field. There are three core ways a model can learn from data, and understanding the difference between them is essential. The first is supervised learning. In this approach, the model learns from labeled examples, meaning every piece of training data comes with both an input and the correct answer already attached to it. For example, in spam detection, each email in the training data is labeled as either spam or not spam, and the model learns to recognize the difference. Another example is price prediction, where historical data includes both the features of a house, like its size and location, and its actual sales price, so the model learns to predict prices for new houses. The second approach is unsupervised learning. Here, the model works with data that has no labels at all. Instead, it tries to find hidden patterns and groupings within the data on its own. A classic example is customer segmentation, where a business has data about thousands of customers but no predefined categories, and the model groups similar customers together based on patterns it discovers, which can then be used for targeted marketing. The third approach is reinforcement learning. This is quite different from the first two. Here, the model learns by receiving rewards and penalties based on its actions, essentially learning through trial and error and feedback, similar to how a person learns to play a video game by trying different strategies and seeing what works. This approach is commonly used in game AI, robotics, and self driving cars, where the system needs to learn optimal behavior through continuous interaction with its environment. Let's now go a bit deeper into deep learning and understand how neural networks are structured. At the most basic level, every neural network has three main components: an input layer, one or more hidden layers, and an output layer. The input layer receives the raw data, for example, the pixels of an image. or the words of a sentence. The hidden layers are where the actual learning and pattern recognition happens through a series of mathematical transformations. And the output layer produces a final result, for example, a classification label or a predicted value. Within deep learning, there are specialized types of neural networks designed for specific kinds of data. The first one shown here is CNN, or convolutional neural networks. CNNs are best suited for images because they are specifically designed to detect spatial patterns like edges, shapes, and textures. This is exactly why CNNs power technologies like face recognition and object recognition. They can identify what's in a photo by analyzing patterns at different levels of detail. The second type shown here is RNN, or recurrent neural networks. RNNs are best suited for sequences data where order matters, such as text, speech, or time series data. Unlike CNN, which look at an entire image at once, RNN process data step by step, remembering information from previous steps to understand context, which makes them useful for tasks like language translation or speech recognition, where the meaning of a word often depends on the words that came before it. Let's now talk about natural language processing, commonly known as NLP. NLP is the branch of AI that lets computers read, understand, and generate human language. And this is exactly the technology behind chatbots and tools like ChatGPT. Human language is incredibly complex, filled with ambiguity, context, tone, and nuance. So, teaching a machine to genuinely understand it is one of the most challenging problems in AI. Let's look at some real applications of NLP. First, we have chatbots and assistants, which use NLP to answer questions in natural language, understanding what a user is asking and generating a coherent, relevant response. This is exactly how tools like ChatGPT and customer service chatbots work. Second, we have translation, where NLP models convert text between languages almost instantly, which is what powers tools like Google Translate. Third, we have sentiment analysis, which is used to detect whether a piece of text, like a product review or a tweet, expresses a positive or negative sentiment. This is extremely valuable for businesses that want to understand customer feedback at scale without manually reading thousands of reviews. And fourth, we have text summarization, where NLP models can condense long documents into a short summary within seconds, saving huge amounts of time for anyone who needs quickly understand the key points of a lengthy report or article. Together, these applications show how NLP has transformed the way we interact with machines using something as natural as our own language. Now let's move to another major field of AI, computer vision. Computer vision teaches machines to interpret images and video, allowing them to recognize objects, faces, and scenes much like the human eye and brain do naturally. Let's explore its key applications. The first is image recognition, where the model's job is simply to label what's in a photo. For example, identifying that a picture contains a dog or a car. The second is object detection, which goes a step further than basic recognition. Instead of just labeling the entire image, it locates and draws boxes around multiple individual items within that image. You can see this illustrated on the slide, where a person, a car, and a sign are each detected separately with a confidence score, like person 0.98, meaning the model is 98% confident that object is a person. The third application is face recognition, which is used to verify someone's identity, such as unlocking your phone just by looking at it, or verifying identity at airport security checkpoints. And the fourth application is medical imaging, where computer vision models are trained to spot tumors and abnormalities in X rays and scans. This is an incredibly valuable application because it can help doctors detect disease earlier and more accurately than manual review alone, potentially saving lives through early diagnosis. Building and training AI models from scratch on your own computer can be slow and resource intensive, which is why most companies rely on cloud platforms. Cloud platforms give engineers instant access to powerful GPUs, pre-trained models, and one-click deployment options, dramatically speeding up the AI development process. Let's look at the three major cloud providers in this space. First is AWS or Amazon Web Services, which offers services like Amazon SageMaker for building and training models, and Amazon Bedrock for accessing powerful pre-trained generative AI models. Second is Microsoft Azure, which provides Azure AI services along with the Azure OpenAI service, giving developers direct access to models like GPT within Microsoft's cloud ecosystem. And third is Google Cloud, which offers Vertex AI as its unified machine learning platform along with access to Google's own Gemini models. The key advantage of all these platforms is that an AI engineer doesn't need to buy and maintain expensive hardware. They can rent computing power on demand, use pre-built models instead of starting from zero, and deploy their applications to millions of users with just a few clicks, which is exactly why cloud platforms have become an essential part of the modern AI engineering workflow. Let's now take a step back and look at how AI is being applied across different industries in the real world, because understanding this context helps you see why this field is so valuable. First, in healthcare, AI is used for disease detection, drug discovery, and smart diagnosis, helping doctors identify illnesses earlier and helping researchers discover new medicines faster than traditional methods would allow. Second, in finance, AI powers fraud detection, credit scoring, and algorithmic trading. Banks use AI to instantly flag suspicious transactions, assess a person's creditworthiness, and even execute trades automatically based on market patterns. Third, in e-commerce, AI drives recommendations, dynamic pricing, and demand forecasting. This is why platforms like Amazon can suggest products you are likely to buy, adjust prices based on demand in a real time, and predict how much inventory they'll need in the future. And fourth, in automation, AI enables robotics. self-driving vehicles, and smart factory workflows, allowing physical tasks that once required human labor to be performed more efficiently and safely by intelligent machines. Seeing these applications across such different industries really highlights that AI engineering isn't limited to tech companies. It's a skill set that's valuable in almost every sector of the economy today. While AI offers enormous opportunities, it's equally important to understand the challenges and risks that come with building these systems responsibly. Let's go through five major challenges. The first is data bias. Since models learn from data, if that data is unfair or unbalanced in some way, the model will inherit and even amplify that bias in its predictions, which can lead to discriminatory or unfair outcomes for certain groups of people. The second challenge is ethics and privacy. This involves getting proper consent before using someone's data, being transparent about how AI systems make decisions, and ensuring AI is used responsibly rather than in ways that harm individuals or society. The third challenge is scalability. It's one thing to build a model that works well in a demo, but serving millions of predictions quickly and cheaply to real users at real world scale is a completely different engineering challenge. The fourth challenge is explainability. This refers to understanding why a model made a particular decision. Many advanced models, especially deep learning models, function like a black box, making it difficult to explain their reasoning, which becomes a serious problem in high stakes areas like healthcare or loan approvals, where explanations are legally or ethically required. And the fifth challenge is data quality. There's a well known saying in this field, garbage in, garbage out, meaning that if the underlying data is messy, incomplete, or inaccurate, no amount of clever modeling can fix the poor results that come out. Being aware of these challenges is just as important as knowing the technical skills because responsible AI engineering requires balancing innovation with caution. So, where is this field headed next? The next wave of AI is moving away from single isolated models toward autonomous multimodal AI systems that can do much more on their own. Let's look at five key trends shaping this future. First is generative AI, which allows machines to create text, images, code, and video on demand rather than just analyzing existing data. This is already transforming creative and technical work across industries. Second are AI agents, which are systems that can plan and act autonomously. Instead of just answering a single question, an AI agent can break down a complex goal into multiple steps and carry them out independently, such as booking a trip or managing a workflow without constant human guidance. Third is multimodal AI, which refers to a single model that can understand and work across text, vision, and audio simultaneously rather than needing separate specialized models for each type of data. Fourth is Edge AI, which means running smart AI models directly on your device like your phone or a smart camera instead of relying on a distant cloud server, which improves speed and privacy. And fifth is responsible AI, which focuses on building safety, fairness, and regulation directly into AI systems from the ground up, rather than treating these concerns as an afterthought. Together, these five trends represent the next frontier that today's AI engineers will be working on in the coming years. Now, for those of you who are seriously considering this as a career, let's talk about the actual roadmap and what kind of salary you can expect. First, let's look at the skills you need to master. Python, which is your foundational programming language, math, and statistics, which form the theoretical backbone behind every machine learning algorithms, machine learning and deep learning, which are the core technical skills for building models, MLOps and cloud, which are needed to deploy and manage models in production, and SQL and data skills, which are essential for working with and querying large datasets. In terms of the actual roadmap, it typically follows five steps. First, learn Python and math to build your foundation. Second, master machine learning and deep learning concepts and techniques. Third, build real projects to apply what you've learned and create a portfolio. Fourth, learn to deploy your models using MLOps practices. And fifth, use all of this is to land an AI engineer role. Now let's talk numbers because I know this is what many of you are curious about. In India, a fresher AI engineer can expect to earn somewhere between 7 to 11 lakhs per annum, while a senior AI engineer can earn anywhere from 35 to 60 lakh per annum. And if you specialize specifically in generative AI, which is currently one of the hottest and most in demand skill sets, salaries can go beyond 80 lakhs per annum. Internationally, in the US, an entry level AI engineer typically earns around $88,000 a year, while a senior AI engineer can earn $215,000 or more annually. These numbers clearly show why so many people are moving towards this career path. The combination of high demand and high compensation makes AI engineering one of the most attractive fields to enter right now. Let's wrap up everything we've covered today. AI engineering is fundamentally about turning raw data into intelligent systems that can see, understand, and make decisions. And in doing so, it is reshaping virtually every industry on this planet, from healthcare and finance to e commerce and automation. We started by understanding what AI engineering actually is and how it bridges the gap between research and real products. We then explored the fundamentals of AI, its different types, and how AI, machine learning, and deep learning relate to one another. We looked at the day-to-day role of an AI engineer, the development life cycle they follow, and the key tools and technologies they rely on. We also covered the three ways machine learn, the structure of neural networks, and two major AI fields, NLP and computer vision. We discussed the cloud platforms that power modern AI development, real world applications across industries, the challenges engineers must navigate responsibly, and where this field is heading in the future. And finally, we walked through a clear career roadmap along with realistic salary expectations both in India and internationally. So, if you're excited about this field, the message is simple. Start learning the fundamentals, build real projects to apply your knowledge, and you will be well on your way to shaping tomorrow's technology. Thank you for watching, and I'll see you in the next video.